Okay, so now we're going to talk about asymptotes of a rational function. Here's the note. We're going to let our function f be p of x divided by q of x. Now remember, a rational function was just a polynomial divided by another polynomial. And so I want it to look like our generic polynomial that we had before. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 all the way down to a sub 0. Remember, that's our generic polynomial from a previous video. Well, I need another generic polynomial down here in the denominator, but I can't use the same letters, otherwise you'd have the same thing divided by itself and just be equal to 1. So to write another generic polynomial, I'm just going to use b instead of a and the letter m instead of n. Alright, so now we're going to refer to pieces of this. Alright, so p of x and q of x, the numerator and the denominator, have no common factors. All that means is that the fraction is completely reduced. Okay, before you apply 1, and 2 here, your rational function needs to be completely reduced. All right, so number 1, the graph of f has vertical asymptotes at the real zeros of q. Okay, so whatever real numbers make your denominator 0, they're going to have vertical asymptotes on the graph there. And that's because, well, if it makes the denominator 0, then we can't use that x value. All right, that was pretty easy to see. Now number 2, the graph of f has one horizontal asymptote or no horizontal asymptote. And those are determined the following way. The degrees of your polynomials. Remember, the degree of the numerator here is n and the degree of the denominator here is m. Alright, so if the degree of the numerator is less than the degree of the denominator, then the graph is going to have just the x-axis, the line y equals 0, as a horizontal asymptote. And that's because, remember, to get horizontal asymptotes, we're trying to determine what happens as x gets really large. And so as x gets really large, if the degree of the numerator is less than the degree of the denominator, then your denominator is getting really large at a much faster rate than your numerator, and so the whole fraction just gets closer and closer to 0. We'll see an example like that in just a minute. If the degree of the numerator and the degree of the denominator are equal, then the graph of f has the line y equals a sub n divided by b sub n. Or in English, that would be the leading coefficient in the numerator divided by the leading coefficient in the denominator. Again, we'll see an example about that in a minute as well. And if the degree of the numerator is greater than the degree of the denominator, then the graph of f does not have a horizontal asymptote at all. And that's because as x gets large, your y values get larger and larger and larger and larger. Let's look at an example. All right, so f of x equals 2x divided by x squared minus 1. I'm going to abbreviate VA for vertical asymptotes. All right, so to find the vertical asymptotes, we need to figure out what real numbers make the denominator 0. So just take your denominator, x squared minus 1, and set it equal to 0. And solve that equation, x equals plus or minus 1. All right, so there are two vertical asymptotes for this function, x equals 1 and x equals negative 1. Right, because those are real numbers. Now for horizontal asymptotes, remember, horizontal asymptotes happen from when x gets really large. And so as x gets really large, we say, well, what's happening? Well, we can also refer back to our thing here. If the degree of the numerator is less than the degree of the denominator, then the graph of f has the line y equals 0, the x-axis, as a horizontal asymptote. So here the degree of the numerator is 1 and the degree of the denominator is 2. So the line y equals 0 is a horizontal asymptote. Now think about it this way. As x gets really large, your denominator gets really large faster than your numerator gets large. You know, because when x is 100 squared is larger than just 100 times 2. And a gazillion squared is quite a bit larger than 2 times a gazillion, so forth and so on. So your denominator is just getting larger at a much faster rate than your numerator, which makes the whole fraction get closer and closer and closer to 0. Follow me? Okay, let's try another one. G of x equals 1 minus 5x divided by 3 plus 2x. All right, so vertical asymptotes. So set the denominator equal to 0, and you get x equals negative 3 halves. So this one's got one vertical asymptote, and it's when x is negative 3 halves. So horizontal asymptote. All right, so look at the degrees again. The degree of the numerator and the degree of the denominator, in this case, are both the same. The degree is 1 for the numerator, and the degree of the denominator is also 1. So the line y equals the leading coefficient in the top, and be careful, that leading coefficient in the top is negative 5. It's just not written in its nice standard form, divided by the leading coefficient in the denominator, which is 2. So y equals negative 5/2 is the horizontal asymptote. Now here's why. As x gets really, really large, we're trying to determine if the y values get closer and closer to a certain number. And in this case, they do get closer to negative 5/2. And you can determine that just by looking at the degrees of the polynomial, and if they're equal, then you just take the leading coefficient divided by the leading coefficient. But you could also rewrite it. And what's the highest exponent out of both the top and the bottom? Okay, just x to the first. So I'm going to multiply the top and the bottom by 1 over x. Okay, if this would have been 5x squared and 2x squared, then we'd be multiplying the top and the bottom by 1 over x squared. Right, whatever the highest exponent is, we're just going to divide the top and the bottom by that value. And everybody agree this is a fancy version of 1, so we're not changing the value of this thing. So what happens when you do that is you get 1 over x minus 5 divided by 3 over x plus 2. And now think about it in terms of x getting really, really, really large. As x gets really, really large, 1 over x gets really close to what number? It essentially goes to 0. 3 over x, as x gets really, really large, it also goes to 0. So really we're just left with 0 minus 5 on the top and 0 plus 2 in the bottom, which is negative 5/2. So as x gets really, really large, these y values for this g function get closer and closer to negative 5/2. Follow me? Okay. All right, so let's try another one. All right, h of x equals negative 2x cubed divided by x squared plus 1. So vertical asymptotes. So take your denominator, set it equal to 0. You get x squared equals negative 1. So x equals plus or minus I. Since there are no real numbers that make the denominator 0, there's no vertical asymptote. Now, horizontal asymptote. All right, the degree of the numerator is greater than the degree of the denominator. So as x gets large, your numerator is getting larger at a much faster rate than your denominator does, which makes the whole fraction get larger and larger and larger and larger and larger. And so there's no horizontal asymptote either. So that's the idea on horizontal and vertical asymptotes. But we've got one other asymptote I want to talk about. All right, make a little note. If the degree of the numerator of a rational function is exactly one more than the degree of the denominator, then the graph of the function has a slant asymptote, also called an oblique asymptote. All right, here we go. So vertical asymptote, x equals 1. Everybody see that? Horizontal asymptote. The degree of the numerator is larger than the degree of the denominator, so none. Does not have a horizontal asymptote. But the degree of the numerator is exactly one more than the degree of the denominator. So there is a slant asymptote. Now make note, to find the slant asymptote, we use long division. Yeah, I know, I hear all the groans out there. We use long division. All right, so we go x minus 1 into x squared. All right, what do we need to multiply this x by to make it look exactly like x squared? Well, you got to multiply by x. So x times x is x squared. X times negative 1 is minus x. All right, go back and change signs. This is the notation I use to let me know that I've done the subtraction. I'm changing signs. The x squareds go away. That was the whole point. And you got an x, so you bring down the x. You say, all right, what are you going to multiply x by to make it look like x? Well, plus 1. So 1 times x minus 1 would be x minus 1. Go back and change signs. And so 1 is your remainder. So the slant asymptote would be y equals, it's always going to be y equals, your quotient, which is x plus 1. So as x gets really, really large, your y values get closer and closer to the line y equals x plus 1. And that's because we actually can take h here and write it as x plus 1 plus 1 divided by x minus 1. From a previous video, remember, we could rewrite this as the quotient plus the remainder. And so as x gets really, really large, this part where the remainder is at, this all just goes to 0. And so the slant asymptote is just y equals x plus 1. Okay, so all you need to do is just do your long division, get down to your remainder. You don't worry about the remainder. You just take the quotient and say y equals the quotient, and that is your slant asymptote. Study well, and please let me know if you have any questions.